In this video, I will be explaining what the Hall effect is and how we can calculate the voltage that it produces. The Hall effect is a voltage that is caused by a current running through a conductor within a magnetic field. When a current is flowing through a conductor normally, the electrons will flow straight through the conductor. But when the conductor is placed into a magnetic field, the electrons flowing in the conductor will feel a force from that field. This magnetic force will cause the electrons to move to one side of the conductor or the other. This will lead to a separation of the charges within the conductor, with the electrons creating a negative charge on one side and a lack of electrons leaving a positive charge on the other. This separation of charges creates a voltage difference between the two sides, and this is known as the Hall EMF. As the current continues to flow, this Hall EMF builds up until the electric force on the charge from the Hall EMF is equal and opposite to the magnetic field force. This is what is known as the Hall effect. Here, we can see an electron moving to the right through a conductor that is in a magnetic field that points into the page. Using the right-hand rule, we can find that the magnetic force on the electron is pointing down. This magnetic force will move all electrons to one side of the conductor, creating a separation of charges. Once the magnetic force and the electric force are equal and opposite, the electrons will have a net force of 0 acting on them, so they will continue to travel in these separated pathways. We can solve for the Hall EMF of specific situations using the magnetic force and electric force equations. We know that once the forces even out, the magnetic force will equal the electric force. We know that magnetic force is equal to charge times velocity times the magnetic field. And we also know that the electric force is equal to charge times the electric field. If we set these equal to each other, we get that QVB is equal to QE. We can then cancel the charge Q from both sides. This leaves us with E equaling V times B. From this, we can see that B is directly proportional to E. So because B is uniform, we can know that E is also uniform. For a uniform electric field, we know that E is equal to the Hall EMF, or epsilon, divided by the width of the conductor. Now, setting our two equations equal to each other, we get that epsilon over L equals V times B. And to solve for the Hall EMF, we can just multiply by L on both sides, and we get the equation epsilon equals BLV, or the Hall EMF is equal to the magnetic field times the width of the conductor times the velocity of the charge. Using this equation, we can calculate for Hall voltages, like in this problem, which says, calculate the Hall voltage induced on a patient's heart while being scanned by an MRI unit. Approximate the conducting path on the heart wall by a wire 7.5 centimeters long that moves at 10 centimeters per second perpendicular to a 1.5 Tesla magnetic field. We will be using the equation that we just solved for, and from the problem, we know that the length is 7.5 centimeters and that the velocity is 10 centimeters per second. It also tells us the magnetic field strength, which is 1.5 teslas. And we will be solving for the Hall EMF. So we can just plug all this information given to us into this equation, making sure to convert our length and velocity units from centimeters into meters. Now, plugging this all into our calculator, we get that the Hall EMF is equal to 0.01125 volts, or 11.25 millivolts of voltage induced on a patient's heart in an MRI.